Thank you very much. So let me start where we stopped last time. First of all, let me say that the sort of handwritten notes of what I'm talking about will appear, or maybe already appeared on the website of the workshop. So, okay, and they contain a little bit more than what I will actually be able to say. So. Okay, so last time I was talking about the AKS Z construction, Alexandrov-Kontsevich-Schwarz-Zaboronsky construction, which sort of provided a unifying, which is a construction of certain class of topological gauge theories in BV formalism from the get-go. And so this is, a certain class, and it contains certain, already a few examples that were known before, and it provides a unifying viewpoint on those examples. In particular, an example of this construction is the Chern-Simons theory, which we'll see in a second. So, so there was a source, a closed-oriented n-dimensional manifold, and a target, which is a Hamiltonian differential graded manifold, or rather exact Hamiltonian differential graded manifold with exact symplectic form. So I fix its primitive 1 form for the symplectic 2 form. So, and it should have a degree or ghost number n-1. And I also want to have a Hamiltonian for the homological vector field on the target, theta. So theta is the Hamiltonian. So it's a function on the target which satisfies the equation that theta Poisson bracket with itself is 0, where this is Poisson bracket with respect to this symplectic structure. So in particular, this means that the corresponding Hamiltonian vector field generated by theta is cohomological, squares to 0. So then there is a natural cohomological vector field on the entire mapping space, which is made out of two ingredients, sort of the source ingredient and the target ingredient. The source ingredient is the lifting of the de Rham operator on M seen as a cohomological vector field on T1 of M. So one can lift that cohomological vector field to the mapping space on one side. On the other side, you can lift Qn to a homological vector field on the mapping space. Adding those together, you get a certain homological vector field on the mapping space. And its generator with respect to a symplectic structure on this odd symplectic structure in this mapping space that we discussed last time. So the generating function, or the Hamiltonian, is this one. So this is the AKSZ action. So here, for each coordinate on the target, you have a corresponding superfield, which is a non-homogeneous differential form. So this number in brackets is the de Rham degree on the source. And I corresponds to a choice of a local coordinate on the target.
Good question. Can I take Lorentz shifted cotangent bundle so that then will be some Poisson structure?
Absolutely, and I'll talk about it in a moment. That's one of the main examples. Absolutely. So, yeah, so examples. Yes, so yeah, and I mentioned in the end of last time that there's a theorem that this action constructed this way satisfies the classical master equation, and somehow it follows from the observation that we took a cohomological vector field on the source, cohomological vector field on the target, lifted both and summed them up. So they, by construction, they anti-commute. They are both, so their sum squares to 0. So if one needs to do a separate check that this is indeed the Hamiltonian for that homological vector field, but knowing that, the fact that it's a generating function for a cohomological vector field implies that S satisfies the master equation. So it's an easy check, in fact. So examples. Well, the first example is something that we have already seen, and it's in some sense a prototypical example, and that's Chern-Simons theory. So here I choose M to be three-dimensional, so I choose n equals 3. So for the target structure, I choose, I take a Lie algebra of some compact group, of some compact Lie group. So little g is the Lie algebra, and I shift it by 1. So, okay, now let's say that to be more explicit, let's fix some orthonormal basis with respect to the Killing form TA, orthonormal basis of generators for the Lie algebra. So, and then let's say that psi A are the corresponding coordinates on this space. So since this space has a shift in it, so those are coordinates of degree +1, or ghost number +1. So then the sort of function theta on the target will be okay, so it's made out of the structure constants of the Lie algebra written in this basis. And I don't care actually about indices being up or down because this is an orthonormal basis, so its placement of indices is kind of decorative. So this is a cubic function that's built in cubic polynomial on the space that's built using the structure constants. Another maybe more elegant way to write it is using some sort of a generating function for coordinates. So if I sum up those over A, so I think of it then as a sort of universal coordinate on n, valued in the Lie algebra rather than valued in numbers. So then I can write this theta in this way. So where this is the commutator, and this in little g, and this is the Killing form in little g. Okay. So that's theta, and the corresponding, okay, the one form alpha is 1/2. Let me just write it using this generating object xi. So the corresponding symplectic form is, well, this one. And, okay, so what should I say here is that the corresponding corresponding vector field which this function generates, the corresponding Hamiltonian vector field, is in fact, so how to write it? So it's xi d over xi, and this is the Chevalier-Eilenberg differential. In which sense? Well, functions on this graded manifold or graded vector space, they are just elements of the exterior algebra of G dual. So that is, functions on n in this case are just Lie algebra cochains or Chevalier-Eilenberg cochains of the Lie algebra, right? So there's a well-known differential here, the Chevalier-Eilenberg differential, and well, this is it. So, okay, so the corresponding superfield, so for each value of the index A, I have a corresponding superfield, and well, relating to the notations from last time, it's A curly with sort of gauge index A. So that's a sum from 0 to 3. It's P-form component. So each of those guys is, so that's a P-form. Well, okay, it's a P-form on M. And its ghost number, so kind of the intrinsic degree, is 1 minus P. So, okay, now I can again sort of consider the sort of universal field, or add together this A times the Lie algebra generator. So this should be curly A. And this is what I denoted last time, A curly without any indices. And this is a differential form on M with coefficients in the Lie algebra with appropriate degree convention. So I should put a shift by 1. Sorry, it's very small here, shift by 1. Okay, and then the corresponding AKZ action, if I just use the formula above and I apply to this case, I will obtain the Chern-Simons action in the BV formalism, the action that I wrote last time. So this action, where A is a non-homogeneous G-valued differential form. So this is a prototypical example of AKSZ construction. So generally, well, AKSZ construction produces these examples where sort of in BV formalism, the field content, so the classical fields, ghosts, and possibly ghosts for ghosts, if there are any, and anti-fields for all of those. So all this field content organizes into non-homogeneous differential forms. So that's sort of the signature property of AKSZ models. So another example that's similar is the BF theory. So BF theory is a relative of Chern-Simons, but they exist for arbitrary value of n. So n here is any. So the target is now, well, an appropriate doubling of the Lie algebra. So I take, again, a Lie algebra. Here, actually, I will not need to use the killing form. So in this example, killing form is not needed. So I take a Lie algebra and then shift by 1, and I add its dual shifted by n minus 2. So let me call, well, an element here little a, and then an element here little b. So then the target data is as follows. So the function on the target is well, this cubic function, which is quadratic in A and linear in B. And alpha is B delta A. So that means that omega is delta B delta A, so these two variables are Darboux conjugate. So the corresponding action, if I use the construction, is the following. So let me call it BF action. So it is the integral over M of, I'll have two superfields now corresponding to these two pieces of the target. So one superfield I will call A and the other I will call B. So A corresponds to this first piece of the target, B corresponds to the second piece of the target. So A is the sum of AP, where P goes from 0 to N, and B similarly, from 0 to N, B, P. And well, the first is a differential form on M with coefficients in G and with shift by 1. So that's actually the same type of superfield that we had in Chern-Simons. And the field B it's also a differential form on M, but with values in G star rather than G, and with a shift n minus 2 rather than 1. In particular, it means that sort of the classical field here, so the field with ghost number 0, is the n minus 2 form with values in G star. And the rest are sort of ghosts and anti-fields. Okay, so back to the action. So the action is B dA plus 1/2 bracket AA. So very similar to Chern-Simons, but well, kind of another field B is used here. And this bracket here is just a canonical pairing between G and G star, so I don't use the killing form here. So this is a BF theory, so it has some history why people got interested in it. For instance, in 2 dimensions, it is 2D Young-Mills in the limit where your surfaces have 0 area. In 3 dimensions, it's a special case of Chern-Simons for a special type of Lie algebra. Okay, now another example. So when you have a Poisson manifold, so this is the well-known example by now, the so-called Poisson sigma model. This is example which works in dimension 2. So the authors, the original authors of this example are Schaller, Strobel, and Ikeda, and this model turned out to be related to Kontsevich's deformation quantization of Poisson manifolds, namely calculating special correlators of boundary observables for this model put on a disk with target your Poisson manifold, calculates the star product. And that was explained in the paper of Cattaneo and Felder from 1999. So in this case, the target is, so you fix some Poisson manifold M, N. So then the target will be like that. So it's a cotangent bundle with a certain shift of the fiber. So the target N is a Poisson manifold. Poisson manifold. So let's call pi the Poisson structure, the Poisson bivector. So here I have, let's say locally I have some coordinates xi on the Poisson manifold and the corresponding fiber coordinates in the cotangent bundle xi I. So okay, now what are this? What is the target data here? So theta is something that actually is a packaging of this Poisson bivector. So namely, in local coordinates, I take the components of the Poisson bivector and I concoct a quadratic function on the fiber in the fiber coordinates. So it has some sort of smooth dependence on the base and quadratic a quadratic function in the fiber. So now the one form is just the standard Liouville one form of the cotangent bundle. So it's let's see xi I dxi, and so the corresponding action, okay, so maybe let me first write down the superfields. So let me call the superfield corresponding to little x. Let me call it capital Xi, and let me for the moment use twiddle to indicate that it is a superfield, so that it has it is a non-homogeneous differential form. So it has components in degrees 0, 1, 2. And also another superfield eta I twiddle corresponding to this xi. Okay, so and then it has also p-form components. Okay, so here there are, okay, in the kind of more physics notations, so the classical field here is the 0 form. So let's call it kind of x or xi, and then there's a it has ghost number 0. Then there is a one form component eta cross, which has ghost number -1. Then beta cross, which has ghost number -2. And here we have the ghost beta, which has ghost number +1 and de Rham degree 0. We have the classical field eta, which has de Rham degree 1 and ghost number 0. And we have the anti-field for x, which has de Rham degree 2 and ghost number -1. Sorry, xi cross, that's an anti-field for x. So, okay, so beta are ghosts, x and eta are classical fields, and the rest are anti-fields for those. So, okay, now the action, the AKSD action, which is, well, the action of the Poisson sigma model in BV formalism, is the integral of well, it's by construction, it's written in terms of the superfields. So eta twiddle I dxi, dx twiddle I, plus 1/2 eta twiddle I, eta twiddle j, pi ij of x twiddle. So maybe it's instructive to write it in components, so let me do that. So, and when you do that, you'll need to sort of understand what does it mean to evaluate your your sort of smooth functions on a differential form. And the idea is that you are sort of, you know what it means to evaluate it on a zero form on the source. And kind of the 1 and 2 form components, so you treat them by Taylor expanding this expression. So then the result is the following. So it's the integral over m. So first let me write down the part which only depends on the classical fields, which will be the kind of the classical action of the model. So there are no twiddles here, so this is the classical action. And then sort of various terms that that come from the BV extension. So there is the term corresponding to gauge transformations. And well, that's corresponding to the gauge transformation of the field eta. And then there's the term corresponding to the gauge transformation of the field x. Then there's a term that corresponds to the commutators of gauge transformations. And then there is a term which is quadratic in antifields. Sorry, there's 1/2 here. Then there's a term quadratic in antifields. And this is the term that sort of corresponds to the fact that this is, so to say, an essentially BV theory. It cannot be treated by, let's say, simpler BRST formalism, which has to do with the fact that actually the gauge symmetry in this model is open. So a commutator of a gauge of 2 gauge transformations is a gauge transformation only modular equations of motion. So in this last term sort of corrects for that phenomenon. So this quadratic term in antifields is a sign that it's an essentially BV theory. So, all right, now those were the examples of the AKZ construction that I wanted to give. Now the next point is fiber BV integrals. So we discussed ordinary BV integrals last time, so integrals over Lagrangians of delta closed half densities or of solutions of the quantum master equation. So there's a fiber integral version of that, which is something that we will need. Fiber BV integrals. They have other names, so other names are BV push forwards, or a more physical name is effective action. Calculating an effective action in the Wilson's sense. So okay, so here the setup is like that. So assume that we have a symplectic orthogonal splitting of the space of fields. So we have our space of fields is split into a Cartesian product, and the symplectic form sort of splits into a symplectic form on F prime and symplectic form on F double prime, sort of pointwise on the product. So at a point, the symplectic form looks like that. So also, let's say that we are in Schwarz's setting with compatible volume element, and let's say that the volume element is also split as a some volume element here and some volume element on F double prime. So I'll be thinking of the splitting as splitting into slow fields and fast fields, or infrared and ultraviolet fields. And this is sort of referring to Wilson's picture of integrating out fast fields and obtaining effective action on slow fields.
Sorry, Pavel, just a question. So, is it already going towards like having the boundary fields and bulk fields, or is it independent?
No. Here I'm not talking about boundary at all. So this is a kind of theory on a closed manifolds, So there are various examples of such splittings. They have nothing to do with boundary. It's more like, for instance, splitting into zero modes and the rest, or splitting, I don't know, differential forms into harmonic forms and sort of the orthogonal complement of harmonic forms. It's more like that.
Okay, so the practical application for this would be like, you want to compute effective action for some given energy scale.
Right. For instance, usually for me it will be something like cohomology. So I can evaluate the perturbative integral over this part, but I cannot over that part. So this is something like zero modes, or I can choose some theta model for zero modes, something that contains cohomology.
Zero modes are sometimes related to like infrared degrees of freedom, and they do have asymptotic boundaries. That is maybe too far.
So, well, here in the setup of a KSD theories, where sort of the kinetic term is governed by the Ram operator, a very natural choice for F prime is actually just harmonic forms.
Okay.
So, okay. Now, given a solution of the quantum mass equation, so given a solution of the quantum mass equation, let's say S on the big space, well, the idea is that I want to push it forward to F prime by integrating out F double prime. One can, I'll push it forward. I don't know, that's probably grammatically incorrect. One can push forward it to an effective action S prime on F prime. And here the idea of the construction is that I want to take the integral of the exponential of this S on the big space. So it depends on the point here, which I can think of a pair, phi prime comma phi double prime. So, okay, and what I should be integrating out, I should be integrating over F double prime. But again, since we are in BV formalism, we should be integrating over a Lagrangian here. And if I'm careful with sort of integration measures, I should take square root of mu double prime and restrict it to L. So, and then the result, well, I want to think of it as the exponential of some induced action or effective action induced on F prime. So phi prime is my infrared field or slow field. So, so this is kind of one way to say it. Another way to say it is that one can consider push forward of at the level of half densities. Can consider push forward of half densities. So let me call it capital P lower star. So I think of P as a projection to the first factor here. Lower star, well, push forward of fiber integral. So, and it goes from half densities on F to half densities on F prime, And well, what it is, I should decorate it with this choice of L actually, which is a decoration of this push forward. So, and it's the integral over a Lagrangian, which, well, takes a half density and produces a new half density. In the example that I'm interested in, it takes the half density e to the I over h s times square root maybe of mu total. And then it goes to e to the I over h s prime root of mu prime. Okay, so this procedure in principle depends on the choice of L.
So this top formula is confusing. How do you know that after you integrate it's e to something?
So
The top formula, e to the IHS S prime, but this looks like it's definition of S prime, right?
right. Here I'm thinking of having some kind of, well, H as a, everything is in a family over H, so this is something that's not dependent on H, right? So, so I should think of this as a, how to say, quasi-classical family.
This is a formal series in 1 over H. Because it's kind of hard to imagine that this can be a definition of S prime.
So if I'm asking that this object does not depend on H prime, then it is a definition. So I can calculate such an integral by, let's say, stationary phase method, right? And I can, so there will be sort of an oscillatory factor in H prime, which I separate, and the part which does not depend on H prime here. So everything should be considered in the family over H prime in the asymptotics. In H bar goes to going to 0. So how else I should say it? I'm fixing some reference volume forms mu prime and mu double prime, and so this is oftentimes this will be just vector spaces. So I can take, I don't know, Lebesgue measure if they're finite dimensional for mu prime and mu double prime. But there is kind of some oscillatory factor here, right? And I'm interested in that. So, okay. Now the statement, there is a statement here which is counterpart of this BV-Stokes theorem for fiber BV integrals. Okay. So the theorem is the following, that, all right. So,
Do you assume anything about the kind of dependence on S on F prime and F double prime? Like, does it factor?
no, it doesn't factor. It's, in fact, it's kind of boring when it factors. Yes. Yeah. So, yeah, no, here actually I'm not assuming anything. When I want to calculate it, let's say by Feynman diagrams or by stationary phase method, then maybe I'm assuming something that this integral is kind of well defined by the, let's say, by Feynman diagrams. So it is, it will be some assumption. But here I'm not assuming anything.
So it starts at some quadratic term?
Yes, and moreover, I'd like this quadratic term to be non-degenerate when restricted here, so which is an interesting part of the assumption. Mm-hmm. Thank you. All right, so now the statement here is, first of all, that this push-forward map acting on half densities is in fact a chain map with respect to BV Laplacians. So these are Schwarz's Laplacians with respect to the appropriate volume elements. So this is a chain map property. So in particular, this chain map property implies that if S was a solution of quantum mass equation, then the effective action will also solve the quantum mass equation. Just if I act with left and right side on the exponential of S, I will obtain that the push forward of S must also solve the quantum mass equation. So this implies that this operation maps solutions of quantum mass equation on F to solutions of quantum mass equation on F prime. Now, another property is the following, that if L and L twiddle are well, homotopic Lagrangians in the sense that I can move one to another by a continuous family of Lagrangians, homotopic Lagrangians, then, and if if I'm given a, sorry, I guess I was talking, yeah, this was defined in terms of half densities, then maybe I should not write mu here, so then this should be the canonical Laplacian, sorry. Then I should be acting on half densities. Okay, I should think of this as a canonical Laplacian then. So, okay, what I wanted to say is that if I have two homotopic Lagrangians and some closed, delta closed half density, then I have the following, that, well, I have two different push forwards of Z, using L and using L twiddle. And they are somehow equivalent. So in which sense they are equivalent? Well, in the sense that they differ by, sorry, for Z was a delta cocycle. So they differ by a delta prime exact term. So this, in the language of effective actions, that means that changing the gauge fixing Lagrangian changes the effective action by a canonical transformation or canonical BV transformation. And I'll say what it is. By canonical transformation. So let me say what is a canonical transformation. So let me maybe say it's a bit easier what is an infinitesimal canonical transformation. So infinitesimal canonical transformation moves S to an expression like that, where R is the generator of the canonical transformation. So I can put some kind of infinitesimal parameter epsilon here. So this is the so-called canonical BV transformation. And then I can have sort of a path of functions S, so that when I move along the path, the derivative looks like that. So that would be, sorry? R is any function, yes. So of degree -1, so I wanted to have degree -1. So another way to say what it is that at the level of the exponentials, I'm changing the exponential by a delta exact term times, well, epsilon here, times R. So for a path, so for a finite canonical transformation, I'm also changing the exponential by a delta exact term. So in fact, this statement implies that 1 and 2 together imply that I can consider solutions of quantum mass equation modulo canonical transformations, and I get a push forward two solutions of quantum mass equation on F prime modulo canonical transformation, and that procedure is insensitive to the Lagrangian, at least as far as I'm changing the Lagrangian in its homotopy class.
So from Schwartz theorem, we know that this last term does not affect the
So, well, actually, it will affect the integral, but the delta will come out. So it will be so since we are not pushing to numbers here, if I change the action upstairs by canonical transformation, then the result will change by canonical transformation downstairs. So if I do the push forward of this object, I will obtain delta prime of something downstairs. Mm-hmm. So it is some sort of a fiber variant of Schwarz's theorem. Yes, oh yes, that's right. If I want to calculate something downstairs, it will not change. If I calculate some number, it will not change that number. That's true. Okay, and here, okay, there is something that sadly I do not have time to explain. I had in mind some example of a fiber integral, which is about BF theory, and so that, let me just draw a pretty picture and leave it at that, this example. So one can study the BF theory on a manifold equipped with a triangulation. And one can sort of consider a splitting of the space of fields of BF theory into cochains of triangulation plus some sort of complement. One needs to sort of make it precise how to include cochains of a triangulation into differential forms and how to choose a complement, and there's a good construction for that. So, for instance, you include cochains by some sort of special piecewise linear forms. And there's also a clever choice of L here, which comes from a construction by Johannes Dupont, which was originally for different differential forms. It's BF theory on a manifold. So in BF theory, I think I already erased it, fields were pairs of differential forms. There was an A field and a B field. They were both n-dimensional, any n. Yes. So then one can push forward two cochains of the triangulation. And one can obtain an effective action which depends on, well, on pairs of A and B field here. Here, A will be, slow A field will be a cochain, slow B field will be a chain of the triangulation.
So F is just forms? What is
It's actually pairs of forms. F prime is pairs of chains plus cochains of the triangulation.
what is the map?
Okay, so this inclusion is it's called Whitney elementary forms, so special piecewise linear forms. There's an inclusion here which is somewhat singular by delta forms supported on the faces of simplices.
Double bracket some complement.
Yes, yes, and yes, it's an appropriate complement.
And how do you know the permanent splits like that?
Oh, because well, it's okay. This construction is done in such a way that omega would split. So yeah, sadly, I'm sort of I don't have enough time to present the details of this construction. Actually, I sketched it in the notes that are shared with you on the website. So there is sort of a neat way to write down such a splitting here. And, well, one can calculate the effective action on this chains, cochains plus chains. And it is somehow local, so it's a sum of, this effective action will be sum of pieces for individual simplices. And, well, one can calculate those pieces, and one, for instance, for one-dimensional simplices, one has some answer that involves Bernoulli numbers. For high-dimensional simplices, one can sort of calculate, but they're less explicit, those answers. So there's an interesting answer here. And if one wants, one can also push down further to sort of cohomology of M. Well, then two copies because there's an A and the B field. And sort of between triangulations, you can also jump between triangulation from a more dense triangulation to a more sparse triangulation by integrating out some redundant fields. So if I have like one triangulation which has some subdivided simplex, I can jump by integrating out fields to a more sparse triangulation. Okay, so let me maybe leave this at the level of these pictures and, well, refer somewhat to these handwritten notes. So, but that is to illustrate the point that the splitting could be interesting, and there are different choices of f prime. So, for instance, here f prime was related to a particular choice of triangulation, and kind of the size of f prime depends on how many simplices I have in my triangulation. So I can have some triangulation with fewer simplices. That would be a small choice of f prime, and that's the ultimate choice, the smallest possible, and that's this one. So in fact, all possible choices of f prime, they organize into a partially ordered set, which has sort of a minimal object. It has sort of a maximal object, the original continuum formulation of a theory. It has some sort of intermediate objects and a sort of minimal object.
There's some nice formula for the effective fraction again.
Right, so in special cases, but well, okay, generally in this example, the tree part of the effective action, so it's given in terms of Feynman diagrams, the tree part of the effective action here is a generating function for Massey operations. And there's a quantum part, the one loop part, which remembers something about Reisinger torsion as a function on the moduli space of flat connections, its expansion near zero connection. So it's something kind of interesting in algebraic topology. Okay, so I hope I don't know, I intrigued you a little bit, but let me, so I promised something in the title of this lecture, so let me, I hope to, I need to tell you something about boundary, so let me proceed to the boundary story. So, okay, let me see. Okay, let me maybe start talking about that a little bit, and then we have a 5-minute break. But let me start. So, field theory with boundary. And I'll start with the classical field theory. So, okay, I want to explain you the classical gauge theory on manifolds with boundary, but before that, let me explain the non-gauge theory with boundary. So on a space-time with boundary. So okay, maybe I need to erase something. Okay, so let's say that I have some kind of space-time manifold M with boundary partial M, and I'm looking at some classical field theory. So it has some space of fields in the bulk. Then let's say that I'm interested in the kind of field configurations restricted to some small neighborhood of the boundary. Let me even say that I want normal jets at the boundary of some high order, or let's say normal infinite jets at the boundary, jets of fields at the boundary. So let me call this space of normal jets of fields at the boundary, let me call it phi pre, because I want to sort of get rid of that. So it's a pre-phase space of the theory. So given a field, I can take its normal jet at the boundary. So I have a projection here. Let me call this projection pi pre. So this space comes with a one form. So this one form is obtained from calculating the variation of the action. So if you look at the variation of the action functional, or I can think of the symbol either as variation or as de Rham derivative on the space of fields. This is equivalent up to some sign conventions, maybe. So you think of delta as either even or odd symbol. And then using Stokes' theorem, I can write the variation as something times the variation of the field without any derivatives hitting it, plus sort of the derivative term, which by Stokes' theorem can be written as an integral over the boundary. So this part here generates the Euler-Lagrange equations. And the remaining part gives me certain one form depending on jets of fields at the boundary. So let me call it alpha. alpha pre. So it's a one form on this space. So, and then I can take its derivative, its de Rham derivative, call it omega pre. So it's delta, it's, oops, for the boundary, and it's the derivative of alpha pre. So, all right. Now the next step is then, okay, so here I want to assume something about this omega, namely that so it's automatically, of course, a closed form, well, it's exact form, but I want to ask that its kernel is a sub bundle of the tangent bundle, and moreover, I want the presymplectic reduction to exist. So then I want to construct this phase space as a presymplectic reduction. So of the reduction of this manifold by the kernel of omega pre. So I want to take the object upstairs and well, identify all points related by moving along the kernel of this omega pre. So this is automatically, so let me assume that this reduction exists. And then it is automatically a symplectic manifold, usually infinite dimensional. So a symplectic manifold. It's symplectic because I just killed the kernel, right? So yeah, I had a presymplectic form, now I have a symplectic form. So it's symplectic manifold. So the phase space. So in nice cases, it is smooth. Okay. I also, so another object that I will need is that, well, I have a sub manifold here given by solutions of Euler-Lagrange equations. So the locus where this parenthesis vanishes. Let me call EL the space of solutions of Euler-Lagrange equations. So, or ELM if I want to be more explicit, so solutions of Euler-Lagrange equations. Then if I, so let me call this composition here. Let me call it pi without pre, just pi. So this composition. So this is a projection. So, and then let me call the projection of EL, let me call it L. So pi of EL of M. So this sits inside the phase space. And let me call it L of M and dm. Okay, so this is somehow the classical dynamical datum of the system. So it's elements of the phase space which extend to field configurations in the bulk solving the equations of motion. And in good cases, this is a Lagrangian submanifold. So this is a little bit of a tricky statement. So it actually has to be proven case by case, depending on the model. So what is true generally is that it's always an isotropic submanifold. Lagrangian property is more tricky and depends on something like some version of Hodge theory working through. So the argument always goes through something like Hodge decomposition theorem. So, but in all the cases that we'll be looking at, it will be a Lagrangian submanifold, and it's actually quite tricky to find examples where you get something that's small, that's isotropic but not Lagrangian. But such examples they do exist, but they are a little bit artificial. So something like a scalar field on a Misner cylinder, so in Lorentzian signature and on a Misner cylinder. So. Okay, maybe let us have a 5-minute break and then we continue with examples here. All right, all right. So let us continue. So a simplest example of the construction on the board there is a scalar field. So scalar field on some Riemannian manifold. So scalar field. So let's say I have a Riemannian manifold MG. So G here is metric, not Lie algebra. So Riemannian n-dimensional manifold. So here, the space of fields is just the space of functions, a space of smooth functions, and the action is, well, let me write the action in the second order formalism. So 1/2 d phi wedge Hodge star d phi. So I'm using the metric for the Hodge star. So, okay, now if I calculate, if I do this exercise over there, if I calculate the variation of the action, which is a very standard exercise to do, so let me very temporarily write down signs, and here I'm thinking of delta, the symbol delta as de Rham operator on the space of fields. So I guess this is massless scalar, massless free scalar, to put all the adjectives. So this will be so I'm thinking of delta as de Rham operator on the space of fields, so it's an odd symbol. And integral for me is a symbol of degree n, or negative n. So, okay, so that will be -1 to the n plus 1 d delta phi wedge star d phi. Right, so because I moved delta past this integral sign, which has degree n, and also past d, so that which accounts for this sign. Okay, so then for this term here, I apply I rewrite it as d of something, d of delta phi wedge star d phi, plus delta phi times d star d phi, and oops, d star d phi, and this last part is also negative star Laplace phi, and this is not BV Laplacian, this is the usual Laplace-Beltrami operator. So, okay, so that means that this calculation gives me the integral over the bulk of Laplace phi delta phi plus a boundary term, the integral over the boundary of star d phi restricted to, so this is an n-1 form in the bulk, so restricted to the boundary times delta phi. So this is this pre-boundary one form. So this entity here, I can also think of it as I take the derivative of phi normally to the boundary, and then I convert this function into an n-1 form on the boundary. So this is the Hodge star on the boundary, associated to the pullback of the metric to the boundary. So partial n means derivative normal to the boundary. So then the corresponding, okay, so this second term gives me the one form, and this is the Euler-Lagrange equation, the vanishing of the Laplace of phi. Yes, yes, and that means that my second step of it there will kill all higher parts. So then my pre-symplectic form, well, it's the derivative of this object, so it's the integral over the boundary, volume form, metric volume form on the boundary, times the delta of the normal derivative of the field, wedge delta of the field. So that means that when I pass to this reduction to the phase space, so this reduction will kill indeed everything higher than the first jet. So it's first normal jets at the boundary. So it is just all pairs of the boundary value of field, which is a function on the boundary, and the normal derivative of the field at the boundary. So all such pairs. So this is just two copies of smooth functions on the boundary, where the first copy is the boundary value of the field, the second copy is the normal derivative of the field at the boundary. So, okay, maybe one more thing to say here. Let's say that my manifold looks like a cylinder, so it is some n-1 dimensional manifold.
The second function is on the boundary.
Yes, also, oh, sorry, they are both in the boundary, sorry, yes. Yes, both, thank you so much, yes, yes, indeed. So, let's say that my M looks like a cylinder, so it's n-dimensional manifold sigma cross an interval, T0, T1. So I'm thinking of some kind of cylinder. So sigma here and an interval here. So then, if I look at this L, so I take all solutions of the Laplace equation in the bulk of the cylinder, and I take on both boundaries, the in boundary and the out boundary, I take the restriction of that function, solving the Laplace equation, and its normal derivative. So that gives me this sub-manifold in this phase space for the boundary, and I can think of that phase space as the phase space for, well, one boundary times the phase space for the other boundary, and to account for the fact that to account for orientations of sigma to the induced orientations from the bulk, I should switch the sign of the symplectic form on one of the factors. So each term here looks like that, with sigma instead of partial m. So I have a Lagrangian submanifold, which is given by, well, pairs field a function on sigma, comma, another function giving me the normal derivative, and another pair here. And such a quadruple of functions on sigma is an element here if I can connect, this data by a solution of the Laplace equation in the bulk. So in other words, I can also describe this Lagrangian as a graph of certain symplectomorphism from this copy of the phase space to this copy of the phase space. So graph of the flow of certain Hamiltonian vector field in time t1 minus t0. So that's just linking to the Hamiltonian description of this field theory. So where xh is the Hamiltonian vector field on phi sigma for a particular function which is a Hamiltonian associated to this action, which is it should be a function here, so it should be some function of the normal derivative of the field and the field itself on sigma. So it's actually this function, and let me write down the second term. Okay, let me write it like that. I hope it's clear what I will mean. So it is just a function of a function on sigma, and so of a pair of function on sigma. One of these functions I call this, the other function I call this. So it's a function on phi sigma. I generate the corresponding Hamiltonian vector field. I take its flow. So this Lagrangian is in fact a graph of this flow. Well, okay, so here it's actually the Legendre transform of this S on a cylinder. So it's a Legendre transform. Okay, so that was an example for, well, that was a construction without kind of dealing with gauge symmetry, like what to do with classical field theory with boundary. But now, what if we have gauge symmetry in the game? So gauge theory on a manifold with boundary. And, well, let's write it in BV formalism. Okay, so this will be a sort of a two-tiered structure. There will be some kind of bulk data and boundary data. So, okay, so the bulk data is the space of BV fields of the theory equipped with, okay, something more. So there will be the function, the action functional, which is a function of the BV fields. There is the corresponding. I'm sorry, apologies. So.
Go back to this formula form. I just
So, sorry.
So we have pairs of functions which give some expression. Or rather, sorry, that is the two form.
Yes, this is a two form. So it's like dp dq, right? So this is p and this is q. Okay. So I have a space of bulk fields, a function on it, which is the action, the usual action, or the BV action rather, which is a function of ghost number 0. I have a cohomological vector field, Q, so square into 0, which has ghost number +1. And I have a symplectic form of ghost number -1. So, okay, symplectic form. So, okay, for the boundary, I have my phase space, which is also equipped with some data. So there will be the ecohomological vector field on this space. There will be a symplectic form, moreover, an exact symplectic form of ghost number 0, and here ghost number as usual is +1. And I also want a generator for Q, a Hamiltonian which generates Q as its Hamiltonian vector field with respect to omega. So this one has degree +1. It's a function on the phase space. And, well, sometimes it's called BFV action. Although maybe action is slightly misleading word here. Well, it is a Hamiltonian for Q. So, okay. So at least it's not action in the sense that we are not going to exponentiate it and integrate over something. That's something that we will not do. Okay. Now, there is also another piece of data connecting the bulk data and boundary data is a projection pi here, like over there. So now the sort of the structure relations, well, one relation I already said, well, Q's should square to 0. Moreover, Q in the bulk should be projectable with respect to pi, so that the derivative of pi applied to Q in the bulk gives me Q on the boundary. So, so push forward by pi or derivative of pi applied to bulk Q gives me the boundary Q. Also, as I said, S boundary is the Hamiltonian for Q boundary, so let me write it here. So delta S boundary is the contraction of Q boundary with omega boundary. So, and then here, instead of the old relation, so previously in BV formalism, we had that Q was a Hamiltonian vector field for S. Here, we don't quite have it. Instead, we have a correction to this formula. So this is the would-be relation, which is wrong in the presence of boundary. In the presence of boundary, we have a correction here, pullback of the boundary one form. So here's the boundary one form. So this is kind of the BV-BFV package, the classical BV-BFV package, the bulk data, the boundary data, and sort of the structure relations. And this is the most interesting structure relation. It links the bulk and boundary data. So I should say that sort of in the non-gauge theory, the counterpart of this relation is exactly that this relation over here. So this is kind of what I wrote here is so this term essentially in a non-gauge theory becomes this term. Okay, so and essentially one constructs this BV-BFV extension of a BV theory by essentially by this construction. So one constructs the phase space in exactly the same way, and it turns out that, well, everything is compatible with Q, so you're automatically obtaining a boundary Q, and then you're looking for its Hamiltonian. So that's roughly how it goes. So there are simple examples of BV-BFV, and there are complicated examples. So complicated examples are gravity, and I don't know anything about it. But so there are works by Alberto Cattaneo and Michele Schiavina and Giovanni Canepa about gravity in this context, but that's a complicated example. I don't want to do complicated examples, I want to do simple examples. So a simple example is Chern-Simons. So okay, so Chern-Simons. So again, now I have an oriented three-manifold with a boundary surface. Oriented three-manifold with boundary surface sigma. Okay. So this is sigma, this is M. Now the space, okay, the bulk data is given by the formulas that we have already seen. So in bulk, we have the space of fields, which is just differential forms on M with coefficients in G and with appropriate shift. So the action is the integral of A 1/2 dA plus 1/6 AA. Let me see, what else did I want to write? So the homological vector field, so I can write it, for instance, as like that. And I have a symplectic form, which is this one. Now, the boundary data, the corresponding boundary data is as follows. So the space, the phase space for sigma is just the differential forms on sigma with coefficients in the Lie algebra and with the same shift. So an element here, so let me call it A sigma. So it's, again, a non-homogeneous form on a surface, so it only has the RAM component 0, 1, 2, with the same shift convention. So zero form has ghost number 1, one form has ghost number 0, two form has ghost number -1. So a sigma is C sigma plus a straight sigma plus a cross sigma. So the RAM degrees 0, 1, 2, and ghost numbers 1, 0, -1. So, okay, the map from differential forms to in the bulk to differential forms in the boundary is just the pullback of differential forms by the inclusion of the boundary. So a natural map. So a restriction of differential forms to the boundary. So so no sort of jets appear here, not even the first jet. So in this example, the first jet appeared as a part of story. Here, not even the first jet, just the restriction. And that is because Chern-Simons action is a first order theory. It only contains first derivative. So, okay, so the boundary action is, in fact, it's given surprisingly by the same formula as here, but with an integral over sigma. And let me write it in components. And let me actually drop the subscript sigma for the components. So it is C dA plus 1/2 AA, which is, of course, the curvature of the connection A, plus the term A cross 1/2 CC. So, so the Q on the boundary is given by the same formula as in the bulk. In particular, Q moves maps C to the commutator of C and C, and maps A to DAC, and maps A cross to the curvature of A plus the commutator CA cross. That's Q sigma. Okay, so that's bulk and boundary data for the Chern-Simons theory. So here I want to make a little digression on BFV construction. So, well, we called it BV-BFV formalism because this boundary package of data, so that is a package that appeared in the literature under the name, well, BFV construction. So that stands for Batalin, Fradkin, Vilkavisky, and that was originally a Hamiltonian reformulation of BV formalism, and then also used sort of in a different context, in the context of symplectic geometry for homological description of coisotropic reductions of coisotropic submanifolds. So let me kind of briefly remark on that. So BFV formalism as a construction for homological resolution of coisotropic reductions. So let's say that I have some ordinary symplectic manifold phi, I don't know, with sort of fat phi with symplectic form omega. So that's ordinary manifold, not graded, and this is an ordinary symplectic structure. So symplectic manifold. And let's say that I have a co-isotropic submanifold. So, right. So, okay. Then we want to describe the coisotropic reduction. So we want to take this submanifold and then consider the restriction of omega to the submanifold, which will have a kernel, and we want to sort of pass to the foliation of C given by this kernel, and will identify points along the leaves. So we want to quotient by the kernel of omega restricted to C. So, okay, so, and then there is sort of a homological construction for describing this reduction. So one looks for a DG Hamiltonian manifold. So let me call it phi, well, let me temporarily write BFV here. Phi BFV, S BFV, Q BFV, omega BFV. So this will be a graded manifold. This will be a homological vector field on it. This will be, okay, a symplectic form of degree 0 on it. And this will be a Hamiltonian for Q. Hamiltonian for Q. So, and then this data is supposed to satisfy some compatibility condition here. So I want the degree 0 part of phi to be my original symplectic manifold. And I want omega BFV restricted to this ghost number 0 part to yield this omega. So omega BFV restricted to this ghost number 0 part should yield the original omega. And okay, so what's the compatibility with C? So I want that the 0 locus of the vector field Q, so points where Q vanishes, again, sort of intersected with phi, I want it to be C. So, okay, so then, okay, let me maybe briefly sort of make a sub remark in order to continue. So given a DG manifold, so a manifold equipped with a cohomological vector field, for a DG manifold, I can look at some point where Q vanishes. So let's say that X is a point where Q vanishes. Then I can linearize Q at that point. So I can take some maybe local coordinate chart around X, so and expand Q in the Taylor series near that point. And the constant term will at X for Q will vanish because, well, Q vanishes at X. So the expansion will start with the linear term. And the linear term, let me denote it Q hat at X. And actually, well, it is, so okay, it's the linear term in the Taylor expansion of Q. So it gives me an endomorphism of the tangent space of phi at X. And actually, this endomorphism doesn't depend on a choice of local coordinates. So the subsequent terms of Taylor expansion depend on local coordinates, but this term doesn't. This term is invariant. And moreover, from the fact that Q squares to 0, this object is a differential of the tangent space to phi. So Q, this linearization, so this Q hat is a linearization of Q at the point X. And it squares to 0, so it gives me a differential on the tangent space. So if I consider also subsequent terms of the Taylor expansion of Q, I get an L infinity algebra on the tangent space, but the first term is just a differential. So moreover, yeah, I can look at the kernel of this differential, and this kernel is the tangent space to the 0 locus of Q. And inside, I have the image of Q hat. And well, again, by sort of staring at the equation that Q squares to 0, these images, they organize into a Frobenius integrable distribution on the 0 locus. So it's an integrable distribution. Distribution on the 0 locus. So then, okay, so returning back to the BFV formalism, what we have is that, okay, so we have the following, that the characteristic distribution, which is the kernel of omega restricted to C at some point x in C. I can understand it as the image of Q hat at x. Well, it's ghost number 0 part, so kind of intersected with well, okay, ghost number 0 part of it. All right. So then the statement is that well, under good conditions, so if the reduction is smooth, one has that the functions on the reduction, I can describe them as zeroth cohomology of Q, acting on the functions on the big graded symplectic space phi. So I have a Q gives me a differential there. I take zeroth cohomology of Q. So and in fact, when reductions are not smooth, then I have sort of the right-hand side exists. So this maybe doesn't exist in the sense of kind of nice geometry, but the right-hand side exists and gives me a kind of homological resolution in the appropriate sense of C underline of the reduction. So if sort of reduction geometrically is something singular, then I can have like cohomology in non-zero degrees here, but the right-hand side is something well defined. So, okay. Now, returning to the Chern-Simons example. So returning to Chern-Simons, to the boundary data of Chern-Simons. So Chern-Simons boundary data. So in this case, if I think of what is the corresponding C, so the zero locus of Q restricted to ghost number 0, so I need to think like where, for which configurations of classical boundary fields Q vanishes, and that is for one-form fields A with 0 curvature. So C is the space of flat connections on sigma, in the flat connections in the trivial G bundle on sigma. So let me write it like that. And this sits inside the symplectic manifold, infinite dimensional symplectic manifold, which is all connections, not necessarily flat, in the trivial G bundle on sigma. So the corresponding distribution, the characteristic distribution on C is given by gauge transformations, identifying, so gauge transformations of flat connections. So when I pass to the reduction, I identify flat connections related by gauge transformations. So C underline in this case is just the moduli space of flat connections in the trivial G bundle on sigma. So this is just moduli of flat connections. So this can be, assuming that G is a simply connected group, I can identify it with group homomorphisms from the fundamental group of sigma to the group modular conjugations by the group. So also I can talk about this construction as a Marsden-Weinstein reduction in the sense that, well, I have the symplectic manifold of all connections, and I have a Hamiltonian action here by well, the group of gauge transformations or automorphisms of my principal bundle. And there is a moment map for this action which sends a connection one form to its curvature. So it maps to two forms on sigma, which I can think of as being a model for the dual of the Lie algebra of gauge transformations. So this is kind of the Atiyah-Bott picture. So this is the Atiyah-Bott moment map. And then in this sense, what we are doing is we are taking the zero level set of the moment map and we are quotienting by the group acting. This is what is denoted, I guess, as, well, symplectic quotient or Marsden-Weinstein quotient. Okay, and here an important remark is that, if we look at the formula for S sigma, then it contains this moment map as a term in the action. So as a term in the BFV action. So plus something else. So let me just leave this observation at that. So there's a term associated to the moment map. So, okay. Now, let me formulate something more general, a more general picture of, okay. So let me formulate a more general picture of sort of induced objects associated with a BV-BFV theory. So sort of associated moduli spaces, or reduction. Okay, so in a BV-BFV theory, I have the space of bulk fields and the phase space and the projection here, and they carry certain supergeometric structure. So here I have the solutions of Euler-Lagrange equations, which is a submanifold here. So here I'm thinking of it as the zero locus of the cohomological vector field Q, the bulk Q. So, okay, so I have a coisotropic submanifold in the boundary phase space, which is the zeros of the Q boundary. So this kind of in terms of classical field theory, it is the so gauge theories sort of in the Hamiltonian picture, they have they induce certain constraints. So this is the constraint surface, or like where constraints are satisfied. So in particular, in order to have a solution of the equation of motion in the bulk in the tubular neighborhood of the boundary, for this to be possible, I need the boundary configuration to be in C. Otherwise, such a solution doesn't exist. But then there's a question of whether a solution in the tubular neighborhood of the boundary exists into the whole M. And this gives me a smaller sub manifold here, which I call LM del M in accord with the notations from before the break. So this is the image of solutions in the bulk under the projection. Right? So those are boundary field configurations which can be extended into the bulk as a solution of equation of motion. So for instance, in Chern-Simons, it would be flat connections on a surface which can be extended flatly into the bulk. And this is actually a Lagrangian in phi. So this C is coisotropic, but this thing, let me write this sort of ugly I don't know, like belongs, it's a seen as a submanifold of the whole phase space, it is Lagrangian. Under certain assumptions, so in good theories, where some version of Hodge decomposition theorem works. So, and then one can pass to a certain reduction picture. So there is something that one can do for any DG manifold, construct certain, construct an associated moduli space of a DG manifold by looking at the zero locus of Q. Where was it? Zero locus of Q. On it I have this distribution given by the linear images of the linearization of Q. So an integrable distribution passed to its space of leaves. So let me call symbolically this is zero of Q modulo Q. So this is some sort of moduli space which you can construct for any DG manifold. So for some details on, this construction in some form was discussed actually in the first pages of the AKSD paper before they came to the construction that we call AKSD construction these days. So I can do this in the bulk for the bulk homological vector field. So, and this will be some sort of reduction of the bulk space of fields. And I can do it in the boundary. So, but just doing the same for the boundary cohomological vector field. So then I have a map between them, which is no longer a projection, but which is induced from this map pi. So let me call it pi push forward. And in fact, what you have under certain assumptions, this sort of Hodge theoretic assumption on the theory, you have the following structure that, first of all, well, this is a symplectic, even symplectic manifold, sometimes with singularities. So this has, this is degree 0 symplectic structure. So underline is just to emphasize that it came from a reduction construction. Upstairs, I don't have actually a symplectic structure, but instead I have a Poisson structure of degree +1, degree +1 Poisson. So, and this comes from a reduction of omega, but somehow omega does not really reduce to a symplectic structure, but well, it reduces to a Poisson structure. So, moreover, the image of this pi star, okay, so this is a reduction of this L by gauge symmetry, essentially. And it is, let me denote it L underline, and it is a Lagrangian submanifold. It's a Lagrangian submanifold in this boundary moduli space. So let's see what else. Yes, also the symplectic leaves of this Poisson structure upstairs are the fibers of the map pi lower star. So this is the picture that we have, sort of remembering this symplectic packages that we had, not just that they were DG manifolds. And so this construction is universal or modulo some Hodge theoretic assumption on the theory. Yes, please? Yes. So, okay, what I mean here is 0 of Q is a sub-manifold inside the space of bulk fields. So Q is a vector field on the space of bulk fields.
The vector field acts on functions.
That's right. That's right. But in particular, I can look at this. I can still look at it as a vector field and see at which points in the space of bulk fields it vanishes. Right? I can still do that. Of course, it's a vector field, so I can think of it as a collection of vectors at points, or as a differential operator acting on functions on that space. Right? Here, Q is a vector field on the space of fields, on the space of bulk fields. So on one hand, I can think of it algebraically as a differential operator acting on functions of bulk fields. On the other hand, I can think of it well, as a collection of vectors, and I can think of points where this vector vanishes. Right? This is the zero of Q, and this means dividing by the image of the linearization. Okay, so example, how this picture works in Chern-Simons theory. Okay, so, all right, so how this, let me just double check. Yes, so example, let's look at Chern-Simons, but let's, for simplicity, restrict to the part of the picture on left and right in ghost number 0. Let's just restrict to that part. Then I have the following. On the left side, the ghost number 0 part of fields is just classical fields, connections in a G bundle, trivial G bundle on M. So the Euler-Lagrange sub-manifold is flat connections. Flat connections on M, so that's my solutions of Euler-Lagrange equations. So on the boundary, I have my phase space is connections on sigma, right? So this is F, and this is the phase space. Inside it, I have my constraint surface, which is flat connections on sigma, so flat connections inside all connections. So this is the constraint surface, so I can take a flat connection and extend it in the thin neighborhood of sigma to a flat connection, to a bulk connection, but only in a neighborhood. I'm not guaranteed that I can extend it into the whole M. But there are those that I can extend into the whole of M. And that's, well, connections on sigma, let me write, M comma sigma, connections on sigma extendable to a flat connection on the entire M. So connections on sigma that can be extended, that, well, have a flat extension over M. So, okay, now the reduced version of this picture, and again restricting to ghost number 0, I have the moduli space of flat connections on M, the moduli space of flat connections on sigma, with its Atiyah-Bott symplectic structure. Upstairs, I cannot write down the symplectic structure because I restricted to ghost number 0, and sort of, these are ghost number 0 coordinates which are paired to ghost number -1 coordinates. So, I mean, there's a Poisson structure upstairs. Sorry, there's no symplectic structure. There's a Poisson structure if I would have retained the parts without the ghost number. So, and then, okay, I have a map here, which is, well, which is a natural map which takes a gauge class of a flat connection to the gauge class of the restricted connection restricted to sigma. But it's not an onto map. So, and I have the image of flat connections in the bulk, and this is L underline M sigma, and this sits as a Lagrangian submanifold in the moduli of flat connections on sigma. So here's an example. If my M is a solid torus, then, well, a flat connection on the boundary surface, on the boundary torus of this solid torus, well, it's prescribed by a pair of holonomies along a pair of cycles, let's say these two cycles, modulo conjugating, so two group elements, modulo conjugating both of them simultaneously by a group element. So then L underline here is given by, such pairs where this holonomy, corresponding to the cycle that can be contracted inside M, is trivial, is 1. So it's gauge classes of flat connections on the two-dimensional torus with trivial holonomy along the contractible circle. Contractible inside M. Right, so this is kind of a half, morally speaking, a half of all moduli space on sigma, more precisely a Lagrangian submanifold. So, and a half in that sense. So maybe I quickly say what happens in abelian theory, but if I retain the all ghost numbers there, it's easier to describe what happens in abelian Chern-Simons. So, okay. So abelian Chern-Simons in the sense that gauge group is R. No, I don't want U1. By abelian, I mean gauge group is R. But let me describe what happens in all ghost numbers. So then I get that on the left side, I have all differential forms on M. That's my space of fields with the shift, with the shift. Inside I have closed forms that corresponds to solutions of the Euler-Lagrange equation. Downstairs I have forms on sigma. Let me drop the shift. The shift is always there. Inside the constrained surface is closed forms. And inside here I have, well, this what I denoted L, which was closed forms on sigma, which can be extended as closed forms on over M, which is a non-trivial subspace here. So, and on the right side, on the level of reduction, I have I have de Rham cohomology of M. Okay, let me write the shift. That's the kind of modular space for the bulk. I have cohomology of sigma as the modular space for the boundary. So the map here is, well, just again, pull back by the inclusion of sigma as boundary into M, acting at the level of cohomology. So this is symplectic graded vector space, where symplectic structure is given by Poincare duality on the boundary. And upstairs I have a degree +1 Poisson structure, which is actually a reformulation of Poincare-Lefschetz duality on M with boundary. So Poincare-Lefschetz duality in particular gives me a degenerate pairing on cohomology relative to the boundary just by integrating a product of two closed forms vanishing on the boundary. So I have such degenerate pairing, and then dualizing it, I have a Poisson structure. So I have a bi vector in H of M tensor H of M. But well, it doesn't correspond to a symplectic structure. Rather, it has symplectic leaves corresponding to these fibers, and you can restore all this picture from the long exact sequence of a pair M, sigma in cohomology of the pair. So let me stop here. Right, thank you.